Hi guys, math for life.
Hashtag math life. That was Miss Espinosa. Today is her 21st birthday. I'm kidding, guys. She's a high school kid. She's 17 today. 18 today. I just know you guys are kids. So I don't know how old, All right, congratulations. Should we leave that in?
Yeah.
Okay, we'll leave it in. All right, guys, L'Hopital's rule. So the ones that we talked about yesterday were indeterminate forms of limit functions of indeterminate forms, or limits of indeterminate forms of 0 over 0 and infinity over infinity. But that doesn't mean those are the only ones that exist. Other indeterminate forms are, we also had an intro, are infinity minus infinity. That's another type of indeterminate form. And then another part of indeterminate form is like 1 raised to the infinity. Sometimes I disagree with this one because 1 raised to anything is 1, but they're talking about limits. And if the value, let's say I have something like this, a to the power b, if the value of a is between 0 and 1, then it's going to converge to 0 because if b is approaching infinity. Because any number that's between 0 and 1, when you square it, when you cube root it, when you raise it to the 4th power, it's an even smaller number. But if the a is larger than 1 and the power b is approaching infinity, then this is just going to keep getting bigger and bigger. Don't worry. We'll talk about it when we get there. What else? What other type of indeterminate forms are there? There is 0 to the 0. What's up?
Would it also be considered for negative 1 to 0? If you're doing it
Negative 1 changes signs every odd or even power. So we're just talking, 1 is a special case. So 1 to the infinity is indeterminate, but 1 itself, if we know for a fact it's 1, it's just going to be output of 1, because no matter what, 1 to anything is 1. Okay. Yeah, okay. All right, here we go. You guys ready?
Yep.
All right, I'm going to look, not all of them. Sometimes, I've taken this quiz many times. There's sometimes one that there is no L'Hopital's rule. I think I took this quiz already 2 or 3 times, and this one right here, all of them I think are L'Hopital's. Some you have to do it over and over again. All right, if I plug in a 0, e to the 0 is 1, 1 minus 1 is 0, and then, what you got to know? ln of 1 is 0, and you know that because all ln graphs look like this. All logs look like this, all of them. So I have 0 over 0, so can I use L'Hopital's rule? Yeah, because ln of 1 is 0. So here we go. So I'm going to take the derivative. So I'm going to write limit as x approaches 0. The derivative of e to the x minus 1 is e to the x over 9 times the derivative of ln of 1 plus x is 1 over 1 plus x. Now I check. I no longer get 0 over 0, so I'm good. If I plug in a 0, e to the 0 is 1. If I plug in a 0, 9 times 1 over 1, which is 1, so 9 times 1 is... Yeah, if I plug in a 0 right here, you get 1 over 1 plus 0, which is 1. So 9 times 1 is 9, so 1/9.
I thought you said like 1 times 0 is 1.
Oh, well maybe I said that, but I'll rewind it and see what I said.
It's probably the same.
All right, here we go. Are we okay with that one, guys? All right, on this one, as you can see, like sometimes they're simple and you don't need to do L'Hopital's rule. I would have never done L'Hopital's rule with this one. I would have just factored the denominator. I easily see that it's a difference of squares. I would have done this. Of course, they want you to do L'Hopital, so we'll do L'Hopital's. I would have done, if I plug direct substitution, I get 0 over 0. So I go x minus 4, and in the bottom I go x plus 4, x minus 4. What factor cancels out? X minus 4, and 4 plus 4? 8. So I see that answer is 1/8. So there it is. But they want me to do L'Hopital's 0 over 0. So here we go. Limit as x approaches 4. 1, I'm taking the derivative of the top. Take the derivative of the bottom. 2x. I do direct substitution now. So 1 over 2 times 4. And look at that. You get 1/8 again. Cool or not cool? Cool. All right. Next one. I'm approaching 0. Remember, any base or any number besides the 0 to the 0. Any number like 7 raised to the power 0 is going to be 1. 1 minus 1 is 0. And I do direct substitution, I get 0. So again, I get 0 over 0. So can I do chain rule? Can I do L'Hopital's rule? Yes. limit as x approaches 0. The derivative of 7 to the x is itself, and then what do I put next to it? Ln of 7. Good job. Times 1. All over the derivative of x is just 1. Are we still okay? Okay. So now I just do direct substitution. And now I can do direct substitution. 7 to the power 0 ln of 7. 7 to the power 0 is just 1. So there it is, ln of 7. Yay or nay? Perfect. All right, let's go to the next one. See, the first 6 or 7 are going to be pretty fast. You don't get to hard ones until like question 8 or 9. So if I plug in a 0 there, I get a 1. I plug in a 0 there, I get a 0. So I get, when I made 1, I said e to the 0 is 1. 1 minus 1 is 0. Numerator is 0, denominator is 0. So I get 0 over 0. Again, you're going to do L'Hopital's. What I would do before doing anything, I would distribute that. So e to the x minus 1 over 7x plus 7x squared. That way you don't have to do product rule. You know what I mean? Just way easier. So now we can take the derivative because we get 0 over 0. Limit as x approaches 0 of itself, e to the x, over 7 plus 14x. And by the way, guys, I have really bad habits. I should be saying that these functions are differentiable and continuous within the domain. I haven't been saying that. I've just been taking the L'Hopital's rule right off the bat. Because it's in determinate form, we can do L'Hopital's rule. Correct? Okay. Now let's see if we can do direct substitution. E to the 0 is 1. So yeah, we can't do L'Hopital's rule anymore because I don't get a 0 over 0 anymore. And I plug in a 0 and then I just get 7. So 1 7. Cool or not cool? Cool. Top, continuous and differentiable for all row numbers. Bottom is continuous, so therefore you're differentiable, or you're differentiable, so therefore you're continuous. So I'm definitely continuous and differentiable at 0. I can do L'Hopital's rule. I get 0 over 0. Why do you get that? Because cosine of 0 is 1. 1 minus 1 is 0, and then 0 squared is still 0. The bottom, 0 to the 4th power is 0. 0 times 3 is still 0. So I get 0 over 0. I can do L'Hopital's. Are we okay? Yeah, no, guys, I'm sorry if I'm going too fast. Here we go. Limit. X approaches 0. I'm taking the derivative. What's the derivative of cosine? Negative sine x. Plus the derivative of x squared over 2 is just x. That's a half, right? 1/2 x squared. 1/2 times 2. You guys see that, right? Okay. And then derivative of 3x to the 4th? Perfect. I'm going to try 0 again. Notice that if I plug in a 0 again, do I get 0 over 0? What's sine of 0? No. Sine of 0 is 0. So do we get 0 over 0? So we can do L'Hopital's rule again. So here, yeah, you can do L'Hopital's rule as many times as you want, as long as you keep getting indeterminate forms. 0 over 0. Cool or not cool? So limit as x approaches 0. What's the derivative of sine x or negative sine x? Negative cosine x plus what's the derivative of x? 1 over 12 times 3? 36x squared. Look at this. You're going to get another 0. Cosine of 0 is 1, but there's a negative in the front. Negative 1 plus 1, is that 0? 36 times 0, is that 0? Do I get 0 over 0? It's indeterminate. Can I do L'Hopital's again? As long as you keep getting 0 over 0 or infinity over infinity, you can do L'Hopital's again. So let's do it again. Limit as x approaches 0. What's the derivative of cosine x? Yeah, negative sine x, but negative times a negative is a... And then, so it's just sine x over 36 times 2. 72x. Again, if I plug in a 0 for sine x, sine of 0 is 0, and 72 times 0 is 0. So you're going to do it one more time. One more time, like Daft Punk says. Do you know who Daft Punk is? Never mind. I shouldn't ask those questions. What's the derivative of sine x? Cosine x. What's the derivative of 72x? Finally, we don't get 0 over 0 anymore because look, on the bottom is a 72. You're done. You're either going to get a 0 as an output or 1 over 72 as an output because it says as x approaches 0. What is cosine of 0? 1. So 1 over 72. Be aware. This probably applies more to BC because I don't see them doing that to you A-Bers over and over again, but this probably applies more to you. They will do this You know, like they want to see if you can apply it over and over. All right, here we go. We got another one. I have 0 times 1, because e to the 0 is 1, minus 0, so I have a 0 on the top. And I have 1 minus 1, so I get a 0 on the bottom, because cosine of 0 is 1. Do I get 0 over 0? Yes. Can I do L'Hopital's rule? Yes. Unfortunately, you're going to have to do product rule in the numerator. It's okay. It's not the end of the world. Limit as x approaches 0. First times the root of the second, e to the 3x times 3. So there it is. First times the root of the second plus second times the root of the first, which is just 1 right there, minus 1 all over 1 minus, oh, not 1, because the derivative of 1 is 0. The derivative of cosine is negative sign, but I have a negative in the front, so it turns to a positive sine of 3x times 3. And I'm going to check. I'm going to plug in a 0 and see what happens. If I plug in a 0, I see that this will be a 0. I'm careful not to set that equal to 0 because I don't want to, I can already see what's going to happen. And I see that I have a 1 right here because e to the 0 is 1. And I see that that's going to be a 1. What's 1 minus 1? 0. And the bottom I have a sign, and sine of 0 is definitely 0. So I have 0 over 0. Can I do L'Hopital's again? Yes. Sorry, bless you. You're going to have to do product rule again with that. So my bad, guys. So limit, yeah, it can get kind of ugly. So it's the algebra that gets ugly. First times root of the second. And I know you can probably put the 3 with the x there, but I'm going to leave it alone. Derivative of 3e to the 3x is 9e to the 3x. Is everyone okay with that? Plus second, 3e to the 3x times the root of the first, 1. Plus, and then it's the derivative of this guy, so it's going to be 3e to the 3x, or e to the 3x times 3. And the derivative of 1 is 0, so there it is. I think I did everything. First derivative of the second plus second derivative of the first plus, yep, I did everything on the top. All over the bottom, the derivative of sine is cosine 3x times 3, and I already have a 3 in the front, so it's going to be a 9. And then I check this to see if this gives me 0 over 0 or some number. So let's see, if I plug in a 0, I see this guy is going to be 0. This guy will be 3. And this guy will be 3 again. Okay, so it looks like we're good now. So I'm going to have 3 plus 3, which is? And then cosine of 0 is 1, and 1 times 9? So 6, 9 reduces to? There it is. Huh. Don't sound sad, guys. Like 6, 2/3. Huh. Cheer up, guys. It's almost Turkey Day.
That's like exactly a week.
Yeah, it's exactly a week. You're right. So in a little bit, we're going to be having a real good time. All right. All right. Here we go. Here we go. Here we go. Arctan of 0. In case you don't remember. All right, guys. Focus, focus. In case you don't remember, this means, well, I guess I'll put question mark. That means tan of some angle equals that question mark. That's what it means. If you don't remember, arctan of 0 is 0. So this, if I do direct substitution, I get 0 over 0. And I really shouldn't be writing equals that. I should just say equals undeterminate form. So it is 0 over 0 in determinate form. Indeterminate form. So here we go. I'm going to take the derivative. Limit as x approaches 0. 3. Do you know the derivative of arctan? Perfect. Over 6 parentheses. This is a 2x, not a 1x, or not x. 1 over 1 plus parenthesis 2x, close it, squared, and you're not done, times 2. If you want to put a 2 over 1 to help you out. Okay, are we okay? Yeah, we're okay. Plug in a 0. If you plug in a 0, I get 3 times 1. So there it is. I can no longer use L'Hopital's rule because I don't get indeterminate form. I have some number. Over, let's see, in the bottom, I get a 0 there. I have 6 times 2, which is 12 over 1. All right, so this is 3 over 12. And 3 goes into 12 how many times? So 1/4. We're going pretty fast. All right. Here's an example.
Infinity? Oh, of infinity over infinity, right?
Yes. But here's what I wanted to say on this one. All right, guys, focus real quick on this one because this one's a pretty big deal. Here's an example where I think you can just use your logic and rates of growth to figure this out. All right, Miss, leave the birthday girl alone so she can focus. All right, so here it is. Ready? All you got to do is ask yourself, what grows faster? Does ln of x grow faster or does x grow faster? X grows way faster than ln. Way faster. Ln, as a matter of fact, grows real slow. So if the bottom grows faster than the top, what is this limit going to be? Yeah, 0. Now, if you want to do it with L'Hopital's, if they're forcing you to do it with L'Hopital's, here's how you would do it. You see that it's indeterminate form, infinity over infinity, and then you would say, okay, well, I don't like that 7. I'm going to bring it up. Limit as x approaches infinity of 7 ln of x over x. Infinity over infinity. So here we go. Limit as x approaches infinity. 7 derivative of ln x is 1 over x over 1. So look what that is. You get, I guess I'll write it one more time. Limit as x approaches infinity, 7 over x. Well, as the denominator gets bigger, 7 divided by a huge number? Yeah, small. It gets small. It approaches 0. That's the smallest it can be, magnitude-wise. Yeah, spit in the ocean. All right, cool or not cool? All right. Yeah, it's supposed to be like this. All right, rewrite this, guys, as this. Limit as x approaches infinity of cosine to the 4x close to the power x. It's supposed to look like that. This is an example of 1 to the infinity, but they don't know if cosine is actually going to be approaching 1 or if it's a slightly number smaller than 1. We can know real quick. Look, it doesn't matter how you cook it. Limit as x approaches... Oh, did I use the wrong word?
No. I just don't think we were expecting you to say cook it.
Oh, okay. Sorry. As x approaches infinity, what's the limit of 4 over x? 0. What's cosine of 0? 1. So this is an example of 1 raised to the power infinity. And I know for a fact that's a 1 to the power infinity because 4 over x, the limit of that, as x approaches infinity is 0. And we know that cosine of 0 is 1. So 1 raised to any number, as long as we know for a fact it's a 1, is going to be 1. Does that make sense? Okay. So this one is 1. Because that's like 1 to the infinity. But now, not all the times this is considered indeterminate. 1 to the infinity is not always 1. And there's a fight. If you Google it, put 1 to the infinity, there's a fight between mathematicians, whether it really is 1 or whether it's 0, whether it's a number. And there's a whole debacle on it.
I want to see what math teachers do.
All right. Yeah, I was going to do that, Len, but that's fine. All right. Here we go, guys. Here we go. You guys ready for this one? Yeah. So as x approaches infinity, I got to put a plus symbol on this one because let's go from one side. If you approach 0 from the right-hand side, this looks like it's positive infinity. And if you approach 0 from the right-hand side, this is also going to be infinity. So it looks like infinity minus infinity. So it is indeterminate. So what you got to do is don't make it look like 0 over 0 or infinity over infinity. So how do you do that? Let's get a common denominator. So I'm just doing algebra right now. 6 over x minus 6, and then cotangent the same thing as cosine over sine, right? So here's what I'm going to do. Multiply this sucker by x over x. Multiply this sucker by sine x over sine x. And then you get something like this. 6 sine x minus 6 cosine x over x sine x. Limit as x approaches 0. Now I get something way better. I get 0 over 0. See, if you put a 0, wait, hold on. Do I get 0 over 0? Oh, there's the next right here. Now it's 0 over 0. Without that x there, it's not 0 over 0. It would have been negative 6 over 0. And you can't do L'Hopital's rule. But now it is. Now it's 0 over 0. This is 0. If I plug in a 0, and this becomes 0 with that x after that 6 there. Cool or not cool? So now let's just do L'Hopital's rule. It is going to be ugly because of this guy. Because of that guy. So I might have to take some of this space over here. So here we go. Limit as x approaches 0. Oh, don't worry about this algebra. Just catch up later on. And check out the intro. It's going to be really cool. All right. So the derivative of 6 sine x is 6 cosine x minus, and I'm just going to do big bracket here. I'm doing product rule. First times derivative of the second plus second times derivative of the first. All over, and there it is, that's it. And now I'm going to do derivative of x sine x. So I'm doing, remember, it's a derivative of the top over the derivative of the bottom. This is not a quotient, you're not doing quotient rule. First times derivative of the second. So first times derivative of the second, sine x, so cosine x, plus second sine x times derivative of the first, 1. And then I check to see if I get 0 over 0 or a number over something. I think this looks like it's going to be 0 over 0 again. Let's see. If I plug in a 0, this is 6. If I plug in a 0, that will be 0. And if I plug in a 0, that will be 6. Yep, look, 6 minus 6. And on the bottom, that's a 0 because of that x there. And that's a 0 because sine of 0 is 0. So do I get 0 over 0? You're going to have to do derivative again. Notice, it's ugly. It's ugly, but it's not hard. It's cumbersome. You guys know that word, right? It just means it's tedious. So here we go. Limit as x approaches 0. And I am getting into this one. Don't worry, we're going to do that one. By the way, AP exam will not test you on this one. They're only going to test you on 0 over 0 and infinity over infinity. So this is harder than any question they would give you on the AP exam. All right, here we go. Derivative of 6 cosine x is negative 6 sine x. Yes. Yes, that would make life easier. 6 cosine, negative 6 cosine, and I just have that. Good job, miss. What about the bottom? Nope, nothing I can cancel. All right, product rule just with this, guys. So first, the negative is still in the front, so there's my negative. And first times derivative of the second. Derivative of negative sine is negative cosine x plus second. I know, guys, I'm being lazy. I'm just putting it in here. Times derivative of the first. I don't see any mistakes. Do you guys see any mistakes? All over, and then I got to do product rule here. First times derivative of the second, negative sine x. Let me know if I make mistakes. Plus second times derivative of the first, and I still have this one. Plus derivative of sine x is cosine x. I think we're good. So let's see. If I plug in a 0, this will be 0 because that's 6x. And this will be, oh, it looks like another 0 there. Let's see, 0. Oh, perfect. I can't use L'Hopital's rule anymore because I get 0 over 2.
That's 0.
And 0 over 2 is? All that for 0. No. Okay. I'll let your professor fight with you. This is 0. This is nothing. That's null. It's super important in programming. Oh, well, I just wanted to let you know. For you, you're going to need it because you're going to be an actuary with programming. For those of you that are going into programming, this is null. In computer language, null means empty. Like there's nothing there to store. This is like a physical, like binary, 0 and 1. Like there's no current. Or there's like, do you guys know what I'm talking about? So for you guys in computer science, that's going to be a huge deal. And I'll let your professor talk to you guys about that. All right, here we go. This is the hardest question in here. All right, guys, this is the hardest question in here. Infinity raised to the 0. That's indeterminate form. Yeah, look, as x approaches infinity, x to the 5th power plus 1, that's infinity. And then 1 over ln of x, well, ln of x, as x gets larger, ln of x will get larger. But 1 divided by a large number is 0. Does that make sense? So what you have here is infinity raised to the 0. That's indeterminate form. Here's how you do it. Don't even mess with this. I would just go to the side and I would go y equals, everything in sky blue is this question. Y equals x to the 5th plus 1. And notice I left a little bit of space. 1 over ln of x. Here's what I would do. Anytime you have an exponent, ln it. So you can bring that exponent down. I'm going to put an ln here. I'm going to put an ln there. When I do that, this 1 over ln x, let me erase this 1 in case you guys think that's part of that, goes down here. That's just the power rule for natural logs. I'm not doing any calculus. I'm just doing algebra right now. So I have this. ln of y equals 1 over ln x, ln of x to the 5th plus 1. So now I'm going to focus on this. Now you really do have, check this out, ln of x to the 5th plus 1 over ln x. Now I really do have infinity over infinity. I'm going to write the word limit as x approaches infinity. Are we okay? Yes. Yeah, I'm not going to worry about that right now. Because if I worry about that side right now, it might be too much. Are we okay so far? All right. So we're focused on the right-hand side. Now remember, this expression is not that. This expression is y, or, y equals x to the 5th plus 1 over ln x. We'll worry about that later. So I have infinity over infinity, which we know it's indeterminate. They can test you on this. And I say, okay, well, I have infinity over infinity. Can I use L'Hopital's rule? Yes, you're differentiable and continuous in its domain. I can use L'Hopital's rule, so I'm going to use L'Hopital's rule. It says that I can go limit as x approaches infinity, and then the derivative of x to the 5th plus 1, or ln of x to the 5th plus 1 is 1 over x to the 5th plus 1 times 5x to the 4th over, and the derivative of ln of x is just 1 over x. Are we okay? Okay, I'm just focused on this here. Are we, nothing crazy, right? So I have, let me rewrite it. Limit, let me go back to red. I have limit as x approaches infinity of 5x to the 4th over x to the 5th plus 1 over 1 over x, which is the same thing as limit as x approaches infinity of, let's see, keep, change, flip, 5x to the 5th over x to the 5th plus 1. Yes.
Oh, because you multiply by x.
Yeah, I said keep, change, flip. Yeah, keep, change, flip, the 1 over x. It's x over 1. And I didn't want to show that step. So, all right. Notice I have this. Hopefully by now there's a whole bunch of red flags in your head. And they're telling you this, as limit as x approaches infinity, is what? 5. Yes or no? Mm-hmm. And everyone's okay with that? Mm-hmm. Okay. And then you're going to go to the answer choices. You're going to say, well, none of them have 5, but the only one that I see that is just a positive 5 is B. Don't use that logic. They'll probably work, but don't use that logic. Here's what you really did. You found the end behavior for ln of y. So I'm going to write EB for end behavior. You found the end behavior for ln of y. Do I want the end behavior for ln of y? No. You want the end behavior for this expression, x to the 5th, I'm going to say it again, x to the 5th plus 1 raised to the power 1 over ln x. You want the end behavior of that. What did I call that in the very beginning? Y. I want the end behavior for y. So you come back over here and you're like, well, that's my end behavior for ln of 5. How do I get y by itself? No, don't say divide. This is ln of an argument. You can't divide by ln. It's not ln times y. E. E and ln are inverses of each other. So you go E to that, and E, whatever you do to one side, you do it to the other. Does that make sense? So now you have, oh, okay, now this is the end behavior for y. Y equals E to the 5th. Remember, this is end behavior. So now can I say what this answer is? Yes, the limit x approaches infinity for y is E to the 5th. So there it is. It's this guy. Does that make sense, guys? Yeah. That's as hard as it's going to get. You're not going to get any harder than that. You now have 2 videos on L'Hopital's rule. You got this one, and you got the video from 3 years ago.
Oh my God.
So I'm going to upload this one. Happy birthday, Mrs. Espinosa. You get a shout out one more time. Does anyone want to say anything to my fans, to our fans?
I love Natalie as well.
Class of 2024 would like to say shout out to Miss Espinosa. And class of 2024 wishes you the Merry Christmas and Happy Thanksgiving and Merry Jesus, and I hope you go to heaven. All right. Good night. Bye.